My name is Seth Eddington. I'm from the University of Illinois at Springfield, and this is my final project for Organic Laboratory for infrared, carbon-13 NMR, proton NMR, and mass spectrometry. So we will start off by looking at mass spectrometry for C3H5BrO2. First thing we need to do is identify our M+ peak. So on this chart for our molecule here, it does not include our M+ peak. So the way we find this is adding up all of the molecular masses for each of the atoms in the molecule. So when we add this up, we get an M+ of 185. So the second thing we do is find our base peak, which is the largest peak in the graph, being this right here. Our base peak is at 73. The third thing we need to do is identify any fragmentation patterns. So we do this by taking our M+ peak of 185, and we will subtract our base peak of 73, which allows us to get a fragmentation pattern of M-112. And then we can also do another one from taking 185 minus 152, which is about right there, and that gives us an M- peak of 33. Next, we identify our DOU, or degrees of unsaturation. So when we do this by taking the equation of 2 times the number of carbons plus 2 minus the number of halogens minus the number of hydrogens, all over 2. So our equation would be 2 times 3 plus 2 minus 1 from our BR minus 5, the number of hydrogens, all over 2. This makes our DOU equal to 1. This means that we could have either one double bond, one ring, or one ring with a double bond. And lastly, we move on to identifying any halogens that we have in our formula, which we do have a bromine. Next, we will be going to infrared spectroscopy. So, this is a chart to show the different zones that will have different functional groups in them. Now for infrared spectroscopy. So now we will need to identify all of the zones that we have. So starting with zone 1, this starts at 3700 and goes to about 3200. So that's zone 1. Zone 2 starts from 3200 and goes to 2700. Zone 3, anywhere from 2300 to 2000. Zone 4, from 1800 to 1600. And Zone 5 is 1600 to 1400. Everything out past Zone 5 is considered the fingerprint region, and we do not pay this any attention. So now in Zone 1, we could find anything from amides to amines and things like that. And we do have a rather large slope in here, but for right now we are going to consider this nothing in our chart. Zone 2, we could find carbon-to-carbon sp3 bonds, which are rather evident of these here. So we may have carbon-to-carbon sp3 bonds. Now, also, this big valley associated with these two peaks are very apparent of alcohols and carboxylic acids. So we might have an OH in a carboxylic acid as well. Zone 3, we can find things such as carbon-to-carbon triple bonds as well as nitriles, but we have nothing here. Zone 4 is a parent of carbonyl groups, and we do have a large peak, so we can expect to find a carbon to oxygen double bond. And then in Zone 5, we appear to have some sort of peak here, but it is negligible, and we consider that we do not have anything in here. And like we said earlier, we do not pay attention to the fingerprint region. Now we are going to go on to proton NMR. This is a chemical shift guide to show possible functional groups in different areas along proton NMR charts. Now for proton NMR for C3H5BrO2. As we can see, we have two apparent peaks here and here. Now, I have labeled these peaks as 3.5 and 2.9, as they are here. And we can see that the integration number is 2 for each of these peaks. So we know we are going to have two different environments that our hydrogens are going to be contained within. So we also know that they are singlets, as we can say. It appears that there are multiple peaks, but these are in fact singlets, and we will see why here shortly. So we will start out by drawing out all of our carbons. So we have one carbon, another carbon, and our third carbon. So with that being done, we have to incorporate all other possible hydrogens as well as the bromine and oxygen. Now we will also use our other findings from our previous graphs of infrared and mass spectrometry to decide what functional groups we will have. And if we remember, we did have carbon-to-carbon sp3 bonds, which we have in our molecule thus far. And we also had a carboxylic acid. Now, it doesn't matter what end we would put our carboxylic acid, but we'll start over here on the left. So, carboxylic acid to an O to an H. So that brings us to now the bromine. Now we'll put the bromine out here on the end to start, and all we have left to do is fill in our hydrogens. We need 4 more because we have one on the left here. So hydrogen here, hydrogen there. Alright, so now as we can see, we have 1, 2, 3, 4, 5 hydrogens, which is good. 1, 2, 3 carbons, which is good. Our oxygens, 1, 2, and our bromine here. So we have included all atoms. Now we have carbon-to-carbon sp3 bonds, and we have our carbonyl here, our double bond oxygen, as well as the overall carboxylic acid from our previous findings. Now as for proton NMR, we do know that both of our environments should have 2 hydrogens apiece. So we also will negate the hydrogen that is bonded to the oxygen from the carboxylic acid. It does not count towards one of the 2 groups. So we will look here as well as look here and call these 2 our 2 groups for proton NMR. Now we can also find out that we have 2 hydrogens in each of the environments, which corresponds with both of our peaks and integration numbers. Now, the blue highlighted environment is closest to the oxygens, which will result in a downfield shift to the left. So we know that this goes to this peak right here. And that leaves us with the last one going to the peak on the right. So with this, we do know that we have the correct structure We've included all of our other findings from mass spec and IR, and we have satisfied proton NMR with this structure. Now we will begin carbon-13 NMR. This is another chemical shift guide to show possible functional groups and things like that. Now lastly for carbon-13 NMR. So as we can see, we have 1, 2, 3 peaks total, which correspond with each of our carbons. And we want to be able to identify which carbon is corresponding with each peak. So the way we will do this is we will start by numbering the different peaks. So starting on the right is 1, 2, and 3. Now, the way that this happens is the carbons that are closest to the most electronegative atom will be considered the farthest to the left peak. So, we have this carbon here, which is directly bonded to an oxygen and double bonded to another oxygen, meaning that it is going to correspond to the farthest left peak, being our number 3. So, this one will become our number 3. Next, we have our carbon here in the middle. It is between 2 different carbons and things like that. We'll leave that one for now. Move on to our last carbon. It is bonded to a bromine, which is much more electronegative than carbons and hydrogens and things like that. So, since it's directly bonded to that, we will consider that one our number 2 peak. And that leaves finally our middle carbon here to be our 1 peak, since it is the farthest away from all electronegative atoms. Now, that has been my presentation for carbon-13 NMR for C3H5BrO2. Thank you very much for watching, and it has been a very fun semester. Thanks.